Welcome to Spring LIB.
A block of mass m is attached to the end of the spring. So I'll draw a diagram of the situation first. So we have like this. It is in the unstressed position right now, and it has got a force constant K. The mass is given an initial displacement, so we'll stretch the mass to some displacement here, and this displacement is x naught, and at this position the block is given some velocity v naught. So a time will come when the block is released that the block is going to go to a point of maximum stretch, which is x max, and it is going to oscillate back and forth in simple harmonic oscillator. So at this position, the energy is kinetic energy, since there is no stretch. At this location here, the energy is kinetic plus we have elastic potential energy. And at this location, we have only elastic potential energy. And in part 1, it says we need to find out an equation for the max speed. So we need to see at which location we have the max speed. It's very obvious that the max speed is at this location, because the only energy of the block here is kinetic energy, and the energy is not shared with any potential energy. So therefore, what we can do is that we can equate the energy 1 with energy 2. So total energy at 1, is E1 is equals to total energy at 2, which is E2. So energy 1 is equals to the kinetic energy, which is equals to half mv max squared. And energy 2, which is the energy at this location, is equals to half mv naught squared plus half k x naught squared. If you solve that, half and half cancels from all the sides, and we are left with an equation mv max squared is equals to m v naught squared plus k x naught squared. Since we need to find an equation for v max, we divide the entire thing by m, and our equation is v max is equals to, I'll just write v max is equals to square root of v naught squared. As you can see, m and m cancels, v naught squared plus k by m x naught squared. So that is our equation for Vmax. All right, for part 2, it says we need to find an equation for the maximum stretch. So in this case, we need to equate the energy at location 2 and location 3. So E2 is equals to E3. At E2, we'll have the energy half mv naught squared plus half m kx squared. This is 3. And at E3, we have the maximum stretch, which is equal to half k f x max squared. Again, half and half cancels from both the sides, and we need to find an equation for x max squared. So we can divide this whole equation by m. But first of all, I need to simplify the equation. mv naught squared plus kx naught squared is equals to k x max squared. We'll divide this whole equation by k, and we get an equation x max squared is equals to x naught squared, because this k and this k will cancel, this one, and we are just left over with m by k v naught squared. So therefore our equation is x max is equal to square root of x naught squared plus m by k v naught squared.